Hey everyone, this is Zainab Zaytoun. In this video, I'll explain the antiderivatives or integration for grade 12 ES, LS, and GS. The objectives of this video is to recall the antiderivatives of functions taken in grade 11, determine the antiderivative of some functions, define definite integrals, and determine the properties of definite integrals. Now, students watching this video should know basic integration taken in grade 11. They should also know the integration by change of variable, exponential and logarithmic functions, inverse of trigonometric functions, like arccosine and arctangent, for example. In this video, I'm assuming that you know very well the material for grade 11, so I'm not going to review it. If you feel that you're not so good with these kinds of integrals or you forgot the material of grade 11, you need to go to my channel, then go to my playlists. You will find several grades there. Go to grade 11 and then you'll find these videos on integrals. If you totally forgot this chapter, you need to watch part 1 and part 2 for this video. If you just want to check or just review it very quickly, part 2 would be enough. If you'd like to receive more videos from me, then subscribe to my channel below. Now these are the basic integrals that you took in the previous year. So the integral of a number is just the number multiplied by x plus c. So for example, integral of 5 is 5x plus c. The integral of functions of the form x to the power n, where n doesn't equal to minus 1, is x power n plus 1 over n plus 1 plus c. So you add 1 to the power and you divide by the new power. So for example, the integral of x squared would be x power 3 over 3. You add 1, so you get 3, and you divide by the new power. And don't forget plus c. The integral of cosine x is sine x, and the integral of sine x is minus cosine x, and plus c for sure. Now, these are some integration that you should know from grade 11, so I'm not gonna solve them. I just wrote them so that you can check if you're good with them or not. If you don't feel that these types of integrals are easy, then I urge you to watch the videos that I showed you in the previous slides. Now let's start with grade 12 material. So you know that the derivative of the exponential function e to the power x is e to the power x, then obviously the integral of e power x would also be e power x. And also you know that the derivative of ln x is 1 over x, so the integral of 1 over x would be ln x. Now for these integrals, you should know them for grade 12, but I'll do a separate short video on integrals only on trigonometric functions, so I'll use them later. So I just want you to know the first two rules for now. Now what's definite integral? So let f be a function defined over an interval I. Big F is one of the integrals of small f, and why we're saying one? Because of the plus c that we write, we have infinitely many antiderivatives. If you recall this from grade 11, so you can replace c by any number and you'll get an antiderivative. So choose any one of them. A and b are two real numbers of the interval I. We denote the integral of f over ab by the integral of ab f of x dx. So what does this definite integral mean, or how do we calculate this definite integral? This definite integral is equal to big F evaluated at b, the upper boundary, minus big F evaluated at a, which is the lower bound. What's big F? As I said, it's one of the antiderivatives. So the easiest antiderivative would be when choosing c equal to 0. So just ignore c. So you need to calculate the integral of f and then evaluated at b minus it evaluated at a. So the first step would be to find the integral of f of x as we did in the previous year. So that's why we add this step. It's just for convenience, so instead of finding the integral separately, you write that it's equal to the integral big f of x, and then you close the brackets and you put the boundaries a, b here. This means that you'll be evaluating this integral at b minus evaluating the integral at a. So let's try to apply this rule. So for example, if you have the integral from 1 to 2 of x dx. So first, you need to integrate x normally. So we add 1 to the power and we divide by the new power. So it'll be x squared over 2. Then you put the brackets and you put 1 and 2 here as this notation. So now this means that you'll be evaluating this integral at 2 minus evaluating this integral at 1 using this rule. So first I'll be replacing x by 2, so you'll get 2 squared over 2 minus the integral evaluated at 1, the lower bound, so it'll be 1 squared over 2. This will give you 3 over 2. So notice that the definite integral will always give you a number. Now this is also an application. Pause the video and try to do them by yourself. The first integral is the integral of cosine x from 0 to pi. So first we find the integral of cosine x, which is sine x, and then we put the brackets and we put the boundaries here. Then we evaluate the integral at pi minus evaluating this integral at 0. So sine pi minus sine 0, you'll get 0. Another example, the integral from 0 to 2 e power x plus 1. Also, the first step is to find the integral and put it between brackets. So the integral of, we know that the integral of e power x is also e power x. So here you'll get 2 e power x. Now we know that the integral of a constant is just the constant multiplied by x. So you'll get 1x, which is x. And notice that I'm ignoring c. So always when calculating definite integrals, you can ignore this c because you only need one antiderivative. Now evaluated at 2 minus the antiderivative evaluated at 0, you will get 2e squared. Now this integral, the integral of 1 over x plus 1 over x squared. By the way, I'm using linearity. It also applies for definite integrals. The integral of 1 over x, we know that it's ln x. So don't confuse between 1 over x and the power rule. So this will give you ln x. Now for this function, 1 over x squared, you should use the power rule. So first you need to take x squared to the denominator or to the numerator, so you'll get x power minus 2 before integrating it. So for the first one, as I said, it's ln x and evaluated at e minus it evaluated at 1 plus the integral of x power minus 2. So we keep this in the integration notation because we didn't integrate it yet. For the first one, we evaluate ln x at e minus ln x evaluated at 1. Ln e is 1, ln 1 is 0, so you get 1. For this one, for the second one, x power minus 2, you use the power rule, so you add 1 to the power and you divide by the new power, so you get x power minus 1 over minus 1. This is the same as minus 1 over x, since you should take this back to the denominator to have a positive power, so it becomes x, and you just take the negative sign before the fraction. Now you've evaluated at e, then minus it evaluated at 1, so you'll get 2 minus 1 over e. Now we will start with the properties of definite integrals. In all the properties that I'm gonna explain or define, we are assuming that the function is continuous over the interval ab. Or more generally, the interval that we're integrating over. So the first property is that the integral from a to a of f of x dx is equal to 0. And this is actually very obvious because if you go back to the definition of definite integrals, then the integral from a to a of f of x would be big F evaluated at a minus big F evaluated at a, which will give you 0. So directly when you see that the boundaries are the same, then the answer would be 0, whatever the function inside the integral is. Now property 2 says that the integral from a to b of f of x dx is equal to minus integral from b to a f of x dx. So here we flip the bounds. So for example, or let's do the proof first. The integral from a to b of f of x dx is big F evaluated at b minus big F evaluated at a. Always when you need to prove any property, you should start from the definition. So this is the definition of definite integrals. Now you need to reach this form. So you need to have f of a minus f of b instead of f of b minus f of a. So this means that you need to take the negative sign common, so you'll get minus, and these flips f of a minus f of b, and then f of a minus f of b is the integral from b to a f of x dx. And here you have the negative sign, because always the first one refers to the upper bound and the second one refers to the lower bound. So here, this means that a is the upper bound and b is the lower bound. Let's do an example that shows that this holds. Let's calculate the integral from minus 1 to 1 of x squared. This should be very easy. You will get 2 over 3. Then integrate x squared from 1 to minus 1. You will get minus 2 over 3. Now the third property, which is on changeless relation for integration. When you have the integral from a to b of f of x dx, it's equal to the integral from a to c f of x dx plus the integral from c to b of f of x dx. So as if you inserted the number, which is c, between a and b. So you choose any number, we call it here c, so it'll be from a to c plus from c to b, like this. But as I said at the beginning of the properties, we're assuming that the function is continuous over the interval that we're integrating on. So it's continuous on the interval AC and CB and AB. Let's prove this property very quickly. So you should either start from this side to reach this side, or start from this side to reach this side. I'll be starting with this side because it's easier, but also this works. So the integral from a to c of f of x dx plus the integral from c to b of f of x dx. Now use the definition. This will give you fc minus fa, and this will give you big F of b minus big F of c. Fc and minus fc will cancel out, and you'll be left with fb minus f of a, which is the integral from a to b of f of x dx. And the proof is done. We'll take this example from Al-Ahliya book. It shows the importance of using this property. So for example, if you're asked to calculate the integral from minus 1 to 1 of the absolute value of x, you don't know how to calculate the integral of the absolute value of x. You need to know when x is negative or when x is positive, so that the absolute value of x would be equal to x, and then you can find the integral very easily. And you need to know when x is negative, so that absolute value of x would be negative x, and also you'll be able to calculate the integral very easily. So look at the boundaries. This is the integral over the interval minus 1 to 1. So for some values which are from minus 1 to 0, x is negative. And for other values from 0 to 1, x is positive. So how can you use this integral to be able to use the information I said now? You can split the integral at 0. So this would be equal to the integral from minus 1 to 0 of absolute value of x dx plus the absolute value from 0 to 1 of absolute value of x dx, using changeless relation. Now over the interval minus 1 to 0, you know that x is negative, so absolute value of x would be negative x. For this integral, it's over 0 to 1, so x is positive, so the absolute value of x is plus x. So you get this form. Now this can be integrated very easily. This will give you minus x squared over 2, and this will give you x squared over 2. Here the boundaries are minus 1 to 0. Here the boundaries are 0 to 1. So you evaluate this at 0, minus it evaluated at minus 1, and same for this one, you'll get 1. The fourth property says that if f of x is greater than or equal to 0 over the interval ab, then the integral from a to b of f of x is also greater than or equal to 0. Why so? Since big F is the integral of small f, then this means that the derivative of big F would be equal to small f. Now we have that f is positive, then this means that big F prime is also positive. If big F prime is positive, so the derivative of big F is positive, this means that the function big F of x is increasing over the interval AB. So since big F is increasing, this means that f of b is greater than f of a, because remember that b is greater than a. So if you have an increasing function and you have two numbers a and b, let's suppose that a is 2 and b is 4 in this case, then for sure f of 4 would be greater than f of 2 since it's increasing. So this will take f of a to this side, so you'll get f of b minus f of a greater than or equal to 0. And this is the same as the integral of f of x from a to b. So it's greater than or equal to 0. For example, the integral from 0 to pi over 2 of cosine x dx is greater than or equal to 0. You can know that it's positive without calculating it, because we know that cosine x in the first quadrant of the trigonometric circle is positive, since here it's from 0 to pi over 2. So for sure the integral from 0 to pi over 2 is also positive. Same for the integral of ex, regardless of the boundaries, because you know that the exponential function is always positive. So the integral of the exponential function over any interval is positive. And it's actually strictly positive. Now, this is a remark. Also, if the function is negative, then its integral is also negative over the interval. The fifth property says that if f of x is greater than g of x over the interval ab, then the integral of f of x from a to b is greater than or equal to the integral of g of x from a to b. Also, let's do the proof. We will start from the given f of x is greater than or equal to g of x. Then take g of x to this side. You will get f of x minus g of x is greater than or equal to 0. Using the previous property, since this is greater than or equal to 0, then its integral is also greater than or equal to 0 over the interval ab. Now you can split this integral using linearity and take this to the other side, so you'll get the property. Let's do this example. Compare the integral from 0 to 1 of x dx and the integral from 0 to 1 of x squared dx. First, according to this property, you need to see which function inside the integral is greater than the other. So we need to look at x and at x squared over the interval 0, 1. So we know that x is greater than or equal to x squared over the interval 0, 1. Then the integral from 0 to 1 of x would be greater than or equal the integral from 0 to 1 of x squared dx. Now property 6 deals with even and odd functions. So you have that a is a strictly positive real number and f is a continuous function over the interval from minus a to a, so two opposite numbers. Then the following properties are admitted. We have that if f is even over minus a to a, then the integral from minus a to a of f of t dt or f of x dx, it's the same, is equal to 2 integral from 0 to a f of t dt. The second one is that if f is odd over the interval minus a to a, then the integral from minus a to a of f of t dt is equal to 0. Actually, this one is very helpful. So when you have an odd function and you have opposite bounds, then the answer would be 0. These are two examples on even and odd functions. So here, notice that you have the integral of x squared from minus 1 to 1. So always when you have, as I said, opposite bounds, you need to think of odd and even functions. The odd function is very helpful. For the even function, it's not always very helpful. So the integral now from minus 1 to 1 of x squared dx, since x squared is even, then this means that it's equal to 2 integral from 0 to 1 of x squared dx. Now the integral of this is very easy and you'll get 2 over 3. If you didn't use the property, you can also calculate this using the definition of definite integrals. So it'll be x power 3 over 3 evaluated from minus 1 to 1. Now, for the second one, also here you have opposite bounds, so you need to think of even and odd functions. So here x power 3 is an odd function, since minus x power 3, minus x in parentheses to the power 3 is equal to minus x power 3. So this means that the answer is 0, simply, without calculating it. Now, when is this very helpful? In this case, you can calculate it and you'll get the same answer. But it'll be helpful in cases of integrals that you don't know how to find the antiderivative of. So for example, if you're asked to calculate this integral, so since you have opposite bounds, you should think if they are if the function inside the integral is odd or even. So suppose that let's name it f of x, so f of x equal this function. Let's check if it's even or odd. It might be neither odd nor even. So f of minus x would be minus x to the power 3 minus into minus x over cosine minus x. This will be minus x power 3 since the power is odd. This will be plus x, and this will be cosine minus x is cosine x. Now, it's not even because it's not the same. Let's try to take the negative sign as a common to check if it's odd. So if we took the negative sign common, we'll be left with x power 3 minus x. So this is minus f of x. This means that f is odd function. And it's also continuous over the interval minus half. Half, because this is the second condition, this means that the integral is equal to 0. So you can see that this property is actually very helpful when the function inside the when you can't integrate the function inside the integral. Now the last property is periodicity. So if f is continuous periodic over R of period t, then the integral from a to a plus t f of x dx is the same as the integral from 0 to t f of x dx. What does this mean? This means if the difference between the boundaries is equal to the period of the function, so here a plus t minus a will give you t, which is equal to the period of the function. It's the same as the integral from 0 to big T f of x. Let's take an example to make it more clear. So if you're calculating the integral of cosine x from 100 pi to 102 pi, since cosine x is a periodic function, you know that cosine and sine are periodic functions of period 2 pi, then you should think of this property. First, you check if the boundaries, if the difference of the boundaries is equal to the period of cosine x. We know that the period of cosine x is 2 pi, and the difference between these two bounds is also 2 pi. So using this rule, it's the same as the integral from 0 to the period, which is 2 pi, of cosine x. Now the integral of cosine x is just sine x, and these are the boundaries, so it's sine 2 pi minus sine 0, which is equal to 0. So actually you're just making the boundaries more simple because you can also calculate the integral from here without changing the boundaries. Same here, try to do this integral by yourself. So since sine x is also periodic of period 2 pi, then check if the difference of the boundaries is 2 pi. Since if the difference is not equal to the period, you can't apply this property. So if you subtract 13 pi over 6 minus pi over 6, you will get 2 pi. So it's equal to the period. So it's the same as the integral from 0 to 2 pi. Now these steps are simple, you'll get 0. And you should write this justification. Thanks for watching, and check my next videos for the rest of this chapter.